Charge on the colloidal particles. Colloidal particles always carry an electric charge. Preferential adsorption of ions on the colloidal particle surface is the most accepted reason to explain the charge on the colloidal particles. For example, we have a silver iodide. This is a neutral colloidal solution, neutral colloidal particle. From the solution, the ionized silver ions and iodide ions, some of the ions can be preferentially absorbed on the surface of a colloidal silver iodide. That gives us a positive charge. That is a most accepted reason for the charge on colloidal particles. Precipitated silver iodide absorb iodide ions from the dispersion medium, and negatively charged colloidal solutions we get. If they absorb silver ions, we get positively charged colloidal particles. That's what we get. We add electrolyte, probably these charges can be neutralized and precipitation do occur. First is called fixed layer. This is the fixed layer. It preferentially absorbed iodide ion here, so negatively charged particles. On addition of a further silver iodide, it gets a second layer, which is known as a diffused layer, silver ions. The combination of the two layers of opposite charges around the colloidal particle is called Helmholtz electrical double layer. In colloidal solution, because of we saw silver iodide has preferentially absorbed iodide, then around this iodide second layer of ions do exist. That's called diffused layer, and the combination of these two layers called Helmholtz electrical double layer. This is how the charges on the colloidal particle we can explain through preferential absorption and diffused layer. If we add in excess of electrolyte, these can be neutralized and we get coagulation or precipitation. Electrophoresis, let's try to understand the effect of electropotentials on colloidal solutions. When we apply electric potential to the colloidal solutions through platinum electrode, the colloidal particles move toward one or the other electrode depending upon the preferential absorption on their surface or what is the charge they carry. If the colloidal particles are negatively charged, they move toward cathode or negatively charged electrode. Sorry, positively charged electrode. In case of negatively charged soles, they move here toward cathode, positively charged electrode. If in electrophoresis, that phenomenon is called electrophoresis, movement of colloidal particles toward electrodes depending upon their charge. Now, if in electrophoresis dispersed particle movement is prevented by some method or mean, it is observed that dispersion medium begins to move in electric field. The phenomenon is called electro-osmosis. So, depending upon electrophoresis and electro-osmosis, the difference is in electrophoresis, colloidal particles do move toward electrode, and in electro-osmosis, our dispersion medium or the solvent moves under the applied electric field. That's the two major difference between these two. precipitation or coagulation. Coagulation is the destabilization of the colloids by the neutralizing the electric charge of the dispersed phase particles, which result in the aggregation of the colloidal particles. The stability of lyophobic soles is due to the presence of charge on the colloidal particles, and once we neutralize those charges, the coagulation do happen or precipitation do happen, as we saw earlier. Stability of the lyophobic soles is due to the presence of charge on the colloidal particles. We can do coagulation through electrophoresis, as we saw here. Just we know electrophoresis, charged colloidal particle will move toward the oppositely charged electrode and get neutralized. And neutralization, because of that, they get precipitated there. Other is, if we neutralize the charges through mixing of oppositely charged soles, if we mix them in the right proportions, we neutralize their charges and get a precipitation. Mixing of a ferric hydroxide sole with arsenious sulphide sole, which is negatively charged, bring them precipitated form. We get a precipitation of. If we dialysis it, dialysis will coagulate. On prolonged dialysis, traces of electrolytes present in solution are removed almost completely, and the colloidal becomes unstable and ultimately got coagulated. Because with the high dialysis, the electrolytes that are responsible for supplying the excess of the charge on the colloidal surfaces are, if completely removed, then what happens? To some extent, neutralization will happen, and there is a result, partial coagulation. Boiling. On boiling of colloidal soles, the adsorbed layer is disturbed due to the increased collision with the dispersion medium particles. So this reduces the charge on the particles and ultimately lead to the settling down in the form of precipitate. So boiling also can neutralize the colloidal particle charges and finally result in precipitation. Electrolytes that we discussed earlier also. Addition of excess of electrolyte causes the colloidal particles to precipitate because the neutralization of the charge. Because the colloids interacting with the ions carrying the charge opposite to the present to themselves, this causes a neutralization and finally precipitation. The ions that carrying opposite charge to the colloidal particles are called coagulating ions. Coagulation by the electrophoresis we just discussed. Colloidal particles move toward the oppositely charged electrodes and get precipitated. If these move here, they get neutralized, and they have no charge now, so they adhere to each other through. Then get precipitated. Mixing of two oppositely charged colloidal soles like ferric oxide and arsenious sulphide, we mixed it up, and then if we mix them in the right proportion, what happens? We saw complete neutralization of both soles charges as they are oppositely charged to each other, and we are getting precipitation. By dialysis, here you see on prolonged dialysis, traces of the electrolyte present in the soles are removed, and that disturbs their absorption charges, and colloids that's why become unstable. We saw here is a concentrated solution. Now here, plenty of electrolytic charges ions are available for absorption on the surface of these that can stabilize because of the colloids of the lyophobic nature are stabilized by repulsive nature with each other, and they got repulsive forces by selectively absorbing negative or positive charges from the electrolytes present in our colloidal solution. Once we start dialysis, these electrolytes start moving out. Once it happens so, now ions available for it are not in that great quantity. That also results in lower amount of charge available on the surfaces of the colloidal particles. So the repulsive forces between the colloidal particles that are stabilizing them, keeping them away from each other, are no longer that strong. That causes these particles to stick together and give us a coagulated mass. By boiling, for example, we heat it up, colloidal particles here, like silver iodide, which having an iodide adsorbed on the surface, and silver ion making a diffused layer. On boiling, we saw adsorbed layers, they get disturbed, they gone. Now the charge on the particles is there is no longer a charge available on it that was stabilizing them. These are gone now. In the absence of such the charges, the particles can stick together and settle down. By addition of electrolyte. On addition of an excess of an electrolyte causes the colloidal particles to precipitate through neutralization. We add the colloidals is again electrolyte we have added, which carrying a charge opposite to our colloidal solution.